Okay, we are off to chapter 8 here, which would again be exam 3 stuff is what this would be. So in chapter 8 here, we're going to talk about chemical composition. We'll talk about a little bit about atomic mass from the periodic table. We'll then talk about really a more usable sort of unit, which is molar mass. We'll also talk about Avogadro's number here in this chapter. And we'll finish up talking about molecular formulas and empirical formulas. So let us get started with first off the atomic mass. So obviously the atomic mass of an atom is based on the number of protons, electrons, and neutrons that there are. Obviously what makes up an atom. But atoms are obviously extremely small, as we talked about, which means you can't really kind of pick one up and just put it on a balance or anything like that. So, how do we get those atomic mass sort of values? And by the way, the atomic mass values are what we see underneath the symbol there on the periodic table. Those numbers on the bottom is what we're really talking about here. So much like in a lot of things, what they did in chemistry is they will typically sort of choose a standard to compare everybody to. Really maybe directly measured. In the case of atomic mass, what they chose was an isotope of carbon, and it was the carbon-12 isotope that they chose. And the carbon-12 isotope has a mass of exactly 12, what I refer to as AMU. And AMU is an atomic mass unit. It is also called a Dalton, although not too many people call it that anymore. It is a unit of atomic mass, and it is technically one way that we can sort of take that information off of the periodic table and use it. For example, if we looked at hydrogen there, the number underneath hydrogen, 1.008. And basically what that means is in hydrogen, there is 1.008 AMU in an atom. Typically speaking, when we do pull off the number, and later here when we talk about really a more usable sort of unit from the periodic table, which is molar mass, we typically take it to 4 significant figures. So depending on your periodic table, there may be a lot of numbers underneath the symbol, or maybe they are rounded a little bit. But typically speaking, whenever you kind of go to the periodic table and you take that bottom number, which either is the atomic mass or the molar mass, usually 4 significant figures is usually how much you want to take. And we could do it for anybody on the periodic table the same way. Again, sodium there, if we looked at it, would be 2299. And that would mean in sodium, there's 2299 AMU in an atom. We could really use it as a conversion factor as well to figure out how much the mass is of a number of atoms in AMU. For example, for hydrogen, we could write it as 1.008 AMU per atom. Or we could use it like a conversion factor of the atom up on top and 1.008 AMU on the bottom. So doing a little dimensional analysis sort of calculation, we could use those figures in a dimensional analysis way. Now, if we do take a peek, though, at something, say, like carbon, it actually says 12.01, which obviously, if they used carbon as the standard, and it has a mass of 12, why do we see sort of 12.01 when we do look at carbon? And the reason for that is what we are actually looking at is the average atomic mass of all the elements that are present. And it's the average atomic mass of all the naturally occurring isotopes. And how we do get some of these sort of calculations is by looking at carbon-12 and going hydrogen's only about 8.4% as large as the carbon-12 isotope. So they could do a little calculation that is 8.4% converted into a decimal, where you move the decimal place, right, 2 places to the left, or divide by 100 to do that. Times it by 12 gives us our 1.008 that we see on the periodic table. Again, like I said, you could really get that number for anybody on the periodic table. And again, the sort of units that we use are one way that we use units are AMU per atmosphere, per atoms. Any questions on that there? So as I was mentioning there, we do see for carbon that it really doesn't say 12, but it does say 12.01. And they are average atomic masses on the periodic table, even though most people don't really call them average atomic masses. But what are they average atomic masses of? They're average atomic masses of all the naturally occurring isotopes for that particular element. So a particular element may have several different naturally occurring isotopes. And what we actually see on the periodic table and what we use for the atomic mass of those elements are really sort of a combination of the masses of all the naturally occurring isotopes. And there is a calculation that you could do to figure out the atomic mass of an element. So if you wanted to figure out the atomic mass in AMU, you would take the percent abundance of the first isotope times the atomic mass of the first isotope. You then would actually add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And depending on your element that you're dealing with, you really just kind of continue that pattern. Depending if there's 3 isotopes, you would do the same thing, obviously, in 4 isotopes. But it is a plus here. And again, people sometimes always want to multiply those numbers together, but you are just going to be adding those guys together. The percent abundance is sometimes called the percent relative abundance, is basically the percentage at which those things occur naturally. So you could have an element that has one isotope that occurs like 70% of the time and another one that occurs about 30% of the time. If you're doing a calculation like this, you would want to make sure, obviously, that all your percentages add up to 100%, right? That means that obviously you have all the naturally occurring isotopes. If it does not add up to 100%, then you probably need to do a little figuring of what the missing percentage is. And you could do that if you have maybe 2 percentages and one they didn't give you the percentage. You could add those percentages together and subtract from 100, right? And that would get you the missing percentage in that case. And again, we do want to make sure that we do convert it into a decimal when you do this calculation, and not leave it in a percentage. So again, either divide the percentage by 100 or just move the decimal place 2 places to the left. So getting back to carbon, carbon has 2 different isotopes that sort of naturally occur, and that is the carbon-12 isotope, which, as we talked about, has a mass of about 12, and the carbon-13 isotope, which has a mass of 13 and some change there. And the carbon-12 isotope occurs about 99% of the time, and the carbon-13 isotope occurs about 1% of the time. So again, if you sort of add up those percentages, it's about 100%, which makes us think that is all the sort of naturally occurring isotopes for that particular element. So that calculation we were just talking about, this is our first isotope. That's 98.89% converted into a decimal by moving the decimal place 2 places to the left, or again, dividing by 100. That is the atomic mass of the first isotope. Once again, here we're then going to add it to the percentage of the second isotope, which is 1.1% converted into a decimal, times the atomic mass of the second isotope, which is 13 and change. And that is how we do get the 12.01 number that we do see on the periodic table, because it really is a mixture, if you will, of those 2 isotopes of carbon. So although, again, like I said, most people will not sort of call it the average atomic mass, it is sort of a combination of all the naturally occurring isotopes. It's important to remember that if you were able to grab up, say, a carbon atom, for example, and put it on a scale and weigh it, you wouldn't find one that has a mass of 12.01. You would really find one that's either the carbon-12 isotope that has a mass of 12 or the carbon-13 isotope that has a mass of 13 and some change there. So we do use it as sort of the mass of the element, and it's sort of a hybrid of average values of all the naturally occurring isotopes. Any questions on that? All right, so why don't you try one here? We have an isotope that occurs about 70.5% of the time and has a mass of 117.8 AMU. The other isotope occurs about 29.5% of the time and has a mass of 120.85 AMU. Calculate the atomic mass, and maybe we can figure out what element it is as well. All right, take a moment or two to see what you come up with. Okay, let's take a look. So once again, we have two isotopes of this particular mystery element here, 70.5% and 29.5. Again, just quickly looking at it, it's about 100%. So we're definitely not missing any isotopes. So we'll do our formula here. We'll take the atomic mass will equal our first isotope. Again, I'm going to move the decimal place 2 places to the left there to convert it into a decimal. That gives me 0.705. We're going to times it by the atomic mass of our first isotope, 11780. We're then going to add it to our second isotope. Once again, we're going to convert that into a decimal, divided by 100 or move the decimal place, times 120.85 here. And that yields us about 118.7 AMU. And if you look on the periodic table, that's about 10, it looks like, maybe. Yeah, it's an atomic mass of 10. Any questions on that calculation there? So again, this is a similar calculation as to how we really do get all the numbers that we kind of see on the periodic table of those averages of the naturally occurring isotopes. Now, AMU is a nice unit and stuff like that, but it's really not necessarily a practical unit that we use a lot in chemistry per se. If you think about when you go weigh something out, right, we usually use grams as sort of the unit that we use when we go to the balance. So although atomic mass in AMU is a nice unit, it's not necessarily one that we use a lot. And there is a relationship between an atomic mass unit and a gram, and you can see it is 1.66 times 10 to the minus 24 grams is the same as an atomic mass unit. All right, we talked about that. So like I mentioned before, we can do some calculations using those values on the periodic table as AMU per atom. So if we went to carbon, as I mentioned before, we could really write two conversion factors for it. 12.01 AMU per atom. R an atom is 12.01 AMU. So if we do sort of a dimensional analysis approach here, 431 atoms of carbon, we would use this guy as our conversion factor where the atoms here will cancel. And that will get us something like 5176 AMU would be the mass of those 431 atoms. Again, not really great for us is like, you know, how many grams is that really? We're not really sure, right, in terms of AMU. So again, we don't necessarily use it all that much, the atomic mass in this type of unit. One more conversion as well. If we went to periodic table and looked underneath aluminum, we would see 2698 listed there, which once again means you could go 2698 AMU per atom, or you could flip it if you needed to. In this case, once again, the atoms of aluminum would cancel if we want to know the mass of our 75 aluminum atoms, and we would end up with about 2024 AMU in this particular case. So as I mentioned, we really do sort of move on from atomic mass and AMU per atom to this more really convenient sort of one, which is molar mass. And that uses units of grams in there, which also uses grams per mole. And that is definitely a much more convenient unit of mass that we use a lot in chemistry. So let's talk about molar mass, which is grams per mole, and Avogadro's number as to what that is. So we're going to start really with Avogadro's number and the idea of a mole. And A mole, which is not the furry guy, but a mole here is a unit in chemistry that does represent a certain amount of something. The abbreviation for mole, as you can see there in the middle, is MOL. So when you do see MOL, that does stand for mole, and it does not stand for molecule, which is a very common mistake a lot of people make. They see that MOL and they think molecule, but it is a abbreviation for a mole. So in life, we have a lot of words that mean something. Like if you have a pair of something, that means 2. If you got a dozen of something, that means 12. If you're old, and they used to give pencils to students, they came in grosses of 144 is what a gross is. Good Jeopardy question, I suppose. So a mole is really sort of the chemistry equivalent to a word that means something. So when somebody says they have a mole of something, what it means is 1 mole really of anything will equal 6.022 times 10 to the 23. A lot of times we look at that and we're talking about atoms, or we may be talking about molecules. This is, as we will see in a second here, what is referred to as Avogadro's number. I almost said avocado. Avogadro's number there is 6.022 times 10 to the 23. And that is basically kind of the numerical value of what a mole represents. So it's sort of like a constant value. You always sort of have that number, Avogadro's number, and what it represents. Now, in chemistry, we do use it, and the units that go with Avogadro's number does change. A lot of times in chemistry, we know we take the 1 moles are 6.022 times 10 to the 23. A lot of times we deal with atoms. The units commonly could be molecules. They could be particles. They could be pizzas. They could be shoes, whatever it may be. Although the occasional pizza does come up in chemistry, but it is usually atoms and molecules that are usually the units that we see the most of the time. Thank you for the non-courtesy laugh. That's okay. All right. So those are typically the ones that we use for most things. What is Avogadro's number really used for? It is the conversion to really go from moles to atoms or molecules, or backwards from molecules or atoms to moles. So we do use Avogadro's number as that conversion of going between moles to atoms or molecules or backwards. And we really use it as a conversion factor. So, we could say there are 6.022 times 10 to the minus 23 atoms over a mole. Or you could use it the opposite way. A mole is 6.022 times 10 to the 23 atoms. And from anybody on the periodic table, we could use sort of Avogadro's relationship. If I had 1 mole of carbon, that would be 6.022 times 10 to the 23 atoms of carbon. If I had 1 mole of iron, that would be 6.022 times 10 to the 23 atoms of iron. You could also apply this to molecules as well and compounds. So if I had 1 mole of water, that would be 6.022 times 10 to the 23 molecules of water. So here we would use molecules because water is not an atom or an element there. It is basically a molecule. So that is how come the units change there. If I had 1 mole of NH3, that would be 6.022 times 10 to the 23 molecules of NH3. And once again, you could write 2 conversion factors for that. 1 mole of NH3 up on top, Avogadro's number on the bottom. Let's write it this way, molecules are 6.022 times 10 to the 23 molecules up on top, and 1 mole of NH3 on the bottom. So we really use it as a conversion factor to do that conversion between those 2 things. One thing that people commonly do is, frankly, they overuse Avogadro's number because they go, I learned that number. Let me just put it in every calculation because that's more chemistry like. So we'll just throw it into every calculation ever known to man. And you really shouldn't do that. You really should only use Avogadro's number in any case where you have a number that's already in atoms of molecules and you need to kind of do a conversion, or you're usually asked to solve for something that has atoms or molecules in it. Otherwise, you really shouldn't use Avogadro's number. So don't just kind of throw it in there for good measure. It has to be some type of conversion where you're going from atoms to molecules, you know, to moles. Any questions on that there? Now, probably a more important sort of conversion that we do a lot in chemistry really does involve molar mass. And molar mass has units of grams per mole. And when we do the molar mass, the number always stays with the grams part, and it's always 1 mole. So we get the molar mass really from the periodic table. And it is the same one that we were just talking about when we called it the atomic mass. But a more convenient unit that we use is molar mass from the periodic table. And you could say for hydrogen that there is 1.008 grams of hydrogen and 1 mole of hydrogen. And that allows you to say that the molar mass of hydrogen is 1.008 grams per mole. Again, it's always the number stays with the grams and 1 mole. You could use that as a conversion factor, again, as 1.008 grams of hydrogen over a mole, or the mole up on top, and 1.008 grams of hydrogen. You could do that for anything that's on the periodic table. If we had 1 mole of oxygen, it would equal 16 grams of oxygen. Again, looking at oxygen on the periodic table, it basically says 16 underneath it. Again, we do take it as 4 significant figures when we pull it off the periodic table, and that means that the molar mass of oxygen is 16 grams per mole is the molar mass, which would give us 2 conversion factors, 16 grams of oxygen per mole, or a mole is 16 grams of oxygen. You could also calculate the molar mass of something that is a compound or molecule. So if I had something like N2O5, we basically would go to the periodic table and add up all the parts. So there's 2 nitrogens. And if we go to the periodic table, nitrogen is 1401 underneath it. So 2 times 1401 plus 5 oxygens, each at 16. And that would get us a molar mass of 2 times 1401 plus 5 times 16, 108.0 grams per mole for N2O5 would be the molar mass of it. Again, we can use it as a conversion factor. Numerically speaking, the atomic mass in AMU per atom and the molar mass in grams per mole works out to be the same number, which is a really nice convenient thing. So when we used it earlier as AMU per atom, that is equivalent to grams per mole in terms of the numbers is basically the same. We do use molar mass the most, and that is usually how we use it in grams per mole. It is the conversion factor to go between grams to moles, or moles back to grams, which is a conversion you do a lot in chemistry. And again, if you just basically need to add up all the parts from the periodic table, and again, that's how many grams there are per mole. Even in a balancing equation that we'll do later, where we have coefficients, whenever you are asked to calculate the molar mass is always strictly calculated from the formula of the compound by itself, regardless of how many of those you have. It's just one individual formula of the compound. Go to the periodic table, add up all the parts, and that gives you the correct molar mass. Any questions on that there? All right. So I'll put this up, but we kind of touched upon it, but this is a mass of a single carbon atom. You can see it's very small mass there. And that's the relationship that we talked about a little bit earlier there for AMU and grams. All right. So as I was speaking about, we use Avogadro's number to do moles to the moles, and the relationship that ties them all together is this. For example, if I had 1 mole of hydrogen, that means that I would have 1.008 grams of hydrogen, and that means I would have 6.022 times 10 to the 23 atoms of hydrogen. So that is the relationship that ties them all together. And just like if you had 1 mole of water, water's molar mass would be 18.02 grams if you looked it up and calculated it. And that would be 6.022 times 10 to the 23 molecules of water. So that is a relationship that basically ties all 3 of those things together. A mole of something is Avogadro's numbers atoms, and a mole of something is a certain number of grams. If I measured out a mole in a beaker of sulfur versus carbon, would it be the same amount? It would not, because a mole of sulfur is 3207 grams and a mole of carbon is 12 grams. So a mole of these individual things do represent a different amount in terms of grams, but they do represent the same amount in terms of atoms that there are. Any questions on that? All right, let's take a look at maybe some calculations here. We want to know how many moles of helium are there in 5.46 grams of helium. And then why don't we also do how many grams are there in C2H6 in let's do 42.5 moles. A number would be good of C2H6. A couple of things that might be helpful in your journey here. Helium on the periodic table underneath says 4.003. Carbon says 12.01, and hydrogen says 1.008. All right, take a few minutes here. First one we're looking for how many moles. Second one we're looking for how many grams. The calculations. So in the first one, we have grams and we want to get to moles. So we're basically going from grams to moles. Do I need to use Avogadro's number here? The answer is no, because there's no mention of atoms, there's no mention of molecules. So the conversion factor that we use to go from grams to moles or moles to grams is the molar mass. And we get that from the periodic table. So in this case, we would go to the periodic table and find that number that's underneath helium. And what that means is helium's molar mass is 4.003 grams per mole, which we could use in that version, or we could flip it around and use it as a conversion factor. And in this case, we could do a dimensional analysis setup here. We would start with 5.46 grams of helium. Once again, grams are up on top, which means to get rid of them, we actually will want to flip the molar mass around so that the grams are on the bottom. We're basically dividing, right, by the grams. The grams of helium will cancel, and we'll take 5.46 and divide it by 4.003. That'll get us a 1.36 moles of helium. Significant figures really based off of the first number there. Yeah. Question on that calculation. So that is a calculation you do a lot in chemistry, taking something from grams to moles. Any questions on that one? Now, the second one is also one that you do a lot in chemistry, which is a conversion really between moles to grams. So in this case, we're actually going from moles to grams. And just like the top one there, there's no mention of atoms, there's no mention of molecules, so we do not use Avogadro's number here. We do not need to do it. We do need the molar mass, so we do need to add up all the parts of this formula from the periodic table. So we would go to carbon, we would go to the hydrogen and do that. And the molar mass here, which we're going to use as our conversion factor for C2H6, there are 2 carbons, each at 12.01 grams per mole from the periodic table, plus 6 hydrogens, each 1.008 from the periodic table. That will give me 2 times 12.01 plus 6 times 1.008, about 3007 grams per mole would be the molar mass here of C2H6. And really that number is our conversion factor. So again, we could treat it like a conversion factor where we take 30.07 grams per mole. Or if we needed to, we could flip it around and do the moles up on top and 30.07 grams on the bottom. In this case, we are starting with 42.5 moles of C2H6. That means we need moles on the bottom, so we will use it as a conversion factor like the molar mass is written. That way the moles will cancel out, gives us 30.07 grams per mole of C2H6. Those guys will cancel. And in this case, 42.5 times 30.707, 30.07. Thank you. And that will be 1277.975 grams of C2H6. In terms of cleaning it up, we would again default back here to the first number, which has a small sig figs, and that is 3. So maybe something like 1280 grams of C2H6 would be the right way to go, as the third sig fig would be right about there. And since that's a 7, we would round that guy up. Yeah. It was in the problem that I made up right there. That we started with 42.5 moles of it. Yeah. Other questions? I almost forgot to put it in there, which is why it's on top there. But yeah, that was that number. So these two calculations, going from grams to moles, moles to grams, is something you do a lot in chemistry. And really all you need is the periodic table. And if it's something that's a molecule or something like that, you just add up all the parts. And that's how many grams there is in 1 mole of that particular substance. Any questions on any of that there? All right, we'll lay it up there for today.